Welcome to this explainer. I'm going to act as your professor today, and together we're going to decode something absolutely massive, the foundational architecture of 2G mobile networks. Whether you're an engineering student, a tech professional, or really just a lifelong learner who looks at their phone and wonders, how on earth does this actually work? Well, you're in exactly the right place. We are going to look at the exact mechanisms that took us from those clunky, static-filled analog radios to the sophisticated global digital networks that run our modern world. Right off the bat, let's dive into this with a truly staggering number, 0.577, specifically 0.577 milliseconds. This infinitesimally small fraction of a second is the literal heartbeat of a 2G network. It's the exact duration of a single time slot, and believe it or not, this tiny window is what keeps our entire digital cellular world from just collapsing into total chaotic interference. By the end of this explainer, you're going to understand exactly why this microscopic number represents a massive leap in human engineering. All right, here is our syllabus for today's masterclass. We're taking a comprehensive, top-down systems approach. First, the digital cellular revolution. Then, we map out the GSM network architecture, organize the airwaves, jump onto the traffic highway, look at mobility and handovers, and finally explore the evolution to packet switching. Section 1. The digital cellular revolution. Let's head back to the 1990s. Now, a core concept that gave 2G its massive capacity is frequency reuse. Honestly, this was a total game changer. Notice how the alternating triangles in this network reuse the exact same frequencies, F1, F2, and F3, but at very specific, carefully separated distances to avoid interference. This brilliant cellular structure allowed networks to serve a huge number of users using a really limited band of radio frequencies. And alongside this capacity came revolutionary features: pan-national roaming, meaning your phone finally worked seamlessly across borders, and digital encryption, ensuring your calls were, for the first time, actually secure. Moving to Section 2, GSM network architecture. Let's map out where your signal actually goes. Making just one single phone call requires a massive, highly interconnected infrastructure. It's basically a giant puzzle divided into three specialized parts. On the left, we have the radio subsystem, or BSS, which talks directly with your phone. In the middle, there's the switching subsystem, or SSS, which acts as the routing brain. And finally, off to the side, we have the Operation and Maintenance Center, the OMC, making sure the whole machine runs smoothly. Let's break these down. Here is a crucial takeaway. Your mobile phone, your mobile station, never talks directly to the broader internet or the main phone network. No way. It first talks to the base station subsystem, the BSS. The BSS is made up of the base transceiver station, or BTS, which are the actual antennas and towers you see on buildings everywhere. Behind those towers sits the base station controller, the BSC. Think of the BSC as a local manager. It controls multiple cell towers, manages the radio links, and makes sure signals are crystal clear before passing them any deeper into the network. Deeper in, behind the towers and controllers, sits the Mobile Switching Center, the MSC. This is the absolute core routing node of the system. If the BTS is the ear of the network, the MSC is the brain. It handles the actual switching of voice calls to connect you to the person you're trying to reach. To pull this off, it relies on two vital databases: the Home Location Register, the HLR, and the Visitor Location Register, the VLR. These instantly verify your identity and figure out exactly where you are on the planet. All right, Section 3, organizing the airwaves. Time to zoom in on the invisible stuff. So how do we prevent millions of signals from crashing into each other? The answer is TDMA, or Time Division Multiple Access. Remember our hook? The network literally chops time into insanely precise blocks. 8 distinct time slots, each exactly 0.577 milliseconds long, get bundled into a frame lasting just over 4.5 milliseconds. Your phone gets exactly one of these microsecond slots to transmit its data before waiting for its next turn. But since radio waves take time to travel and you might be moving, the network inserts guard periods between these slots. These brief pauses prevent overlapping signals, burst alignment errors, and handle time dispersion on the path, ensuring your data doesn't accidentally smash into someone else's. Section 4. The traffic highway. Let's make sense of how data travels in these micro slots. To really grasp this, think of the radio frequency itself as a physical channel. It's the paved road linking your phone to the tower. But a road is pretty useless without traffic, right? The logical channels are like the specific vehicles driving on that road. Just as a real highway has cargo trucks for heavy transport and police cars for directing traffic, our digital network completely separates its channels based on their specific function. First up, the cargo trucks. These are your traffic channels. Their one and only job is to carry your actual digital voice data. You have full rate channels pushing data at 13 kilobits per second and enhanced full rate at 12.2 kilobits per second for even clearer audio. But hey, what if the network gets super congested, say at a packed stadium? The system can instantly deploy half-rate channels. By literally cutting the data rate in half, they double the network's capacity on the fly, so more people can make calls at the same time. Pretty smart. Next, we have the police cars. These are the control channels, and they manage the entire system. Without them, your phone is completely blind. The synchronization channel continuously transmits the frame number to keep your phone perfectly timed to those 0.577 millisecond slots. The broadcast control channel acts like a beacon, broadcasting location parameters. When someone calls you, the paging channel alerts your specific device, and when you want to make a call, your phone hits the random access channel to request an uplink. It is a beautifully choreographed digital dance. Section 5. Mobility and handovers. What happens when things are in motion? It's one thing to stand still, but what if you're literally driving down a real highway while on a call? This is where the magic of mobility management steps in. The network has to constantly know your location to route calls to you. As you travel, your phone detects a change in your location area and immediately requests an update. Behind the scenes, the network updates those visitor databases. It performs a temporary identity reallocation to keep your privacy intact and strictly authenticates your device to make sure you're legit. And the best part? All of this happens totally invisibly in the background. Okay, so what happens when your car drives out of range of one cell tower and into another? The network has to physically transfer your active call without dropping it. This is an intra-BSC handover. Your phone is constantly measuring signal strength. The second the old tower gets too weak and the new tower gets strong enough, the base station controller seamlessly commands your phone to switch its radio frequency to the new tower. It's like a perfect digital baton pass. But what if you travel further, say from one city to another? You aren't just changing towers, you are leaving the jurisdiction of an entire local switching center. The system has to execute an inter-MSC handover. Just look at the sheer complexity here. It's a massive relay race. The old mobile switching center has to negotiate with a completely new mobile switching center. It reserves channels, passes over your subscriber data, and physically reroutes the circuits from the old path to the new path, all in a fraction of a second, so your conversation doesn't even stutter. Finally, Section 6. Evolution to packet switching. How did this voice network adapt to the internet? Those early digital networks used circuit switching. When you made a call, a dedicated point-to-point connection was locked down just for you. But honestly, that's incredibly inefficient for internet data, which comes in quick, unpredictable bursts. So the leap to 2.5G required a massive shift from circuit switching, known as HSCSD, to shared packet switching, known as GPRS. Packet switching is point-to-multipoint. It breaks data down into tiny packets and shares the network channels among multiple users. By bundling up to 8 time slots together and using new coding, GPRS pushed mobile data speeds up to what was then a totally blistering 171 kilobits per second. But here's the catch. You couldn't just run packet-switched internet traffic through the old voice switches. To make this leap, engineers literally had to install completely new, physical packet-switched hardware right alongside the legacy circuit-switched elements. They added a packet control unit, or PCU, to the local controllers, and they dropped in entirely new routing brains, the SGSN and the GGSN. These new nodes completely divided the labor of the early internet. The serving GPRS support node, the SGSN, took over routing and mobility management specifically for data. Think of it like the old voice MSC, but for tracking your location as you download files. Meanwhile, the gateway GPRS support node, the GGSN, acted as the heavy-duty gateway to the outside internet. It handled the vital stuff, screening through firewalls, protocol translation, and of course, the billing support, so your carrier knew exactly how many megabytes you were gobbling up. Perhaps the most impressive engineering feat of this entire evolution is highlighted right here: backward compatibility. Phase 2 was entirely compatible with Phase 1. Think about that for a second. Engineers successfully grafted a brand new packet-switched data network directly onto the existing infrastructure. You could access the internet via GPRS on your shiny new phone without breaking the legacy voice infrastructure that millions of older phones were still relying on. It was literally like changing the engine of an airplane while it was still flying. As we wrap up this explainer, I want to leave you with a question to ponder. We've gone from 0.577 millisecond time slots and 13 kilobit voice channels all the way to the gigabit, purely packet-switched 5G networks in your pocket right now. But how did the rigorous, mathematical foundation of 2G lay the absolute groundwork for everything we use today? Think critically about how organizing the airwaves, managing mobility, and packetizing data, these fundamental, brilliant building blocks, continue to shape the vast digital ecosystem we inhabit. Keep learning, keep questioning,